Today we'll be looking at putting a machine learning system into production. Basically, one of the biggest problems we have with these kind of systems is just the ability to create a scalable machine learning pipeline apart from just a data science project that we started from, and having it put into a production system which can keep refreshing itself and overall actually be of use instead of just an experiment. So the particular use case we have taken today is we are doing component life prediction, and the whole point is, so we are going to talk about the life cycle of this entire component life prediction system, and how about we went in creating it, and just making sure that it remains in production afterwards. So overall, what's happening is, um, we have a bunch of components. They fail at different intervals, and they keep getting replaced. And we're just trying to figure out what their lifetime is for that particular component. For example, a particular, let's say, component A. Component A might run for 800 hours. The next time it might run for 850 hours, and this is because of how heavily it is being used, what stress it is under, and other factors like that. So this system does all of that, and it keeps retraining itself, refreshing itself over time. And right now, this system that we are talking about is actually in production, in use, over 50 rigs across the US and Canada. And this entire system took less than a year to build, considering we started off from very less data, and also we actually had to put in good data collection practices as well. So in this particular case, the biggest challenge that we have, so let's start from step one, right? That is the data. And the biggest challenge we had is uh, actually trying to use EDR data, which is their drilling records. So basically, for a particular component, um, it just gives you basic information about its various factors, like how long it has run, and how much stress it has seen, and things like that. This is raw data, and the thing is, for this system, we had around like 900 million data points, whose data we had to ingest. So there were obviously a lot of anomalies in there. So we actually had to put systems in place to generate high quality data from that, which went far beyond just our normal cleaning of nulls and things like that. We basically had to put in correction algorithms to make sure we could consolidate multiple data points into a single one over time. And another thing that we did over here was, basically, now we have data of a particular system running. We just don't know when a particular component was replaced, under what situation was it replaced, and things like that. So we built another thing called maintenance logs. So the whole point was just to make it as easy as possible for you to collect data, right? And so you can think of that from a form like this, which is this is called a logbook right now. But you can see components being changed, mud temperature, alarms, and things like that. So overall, this this particular portion made our collection of data very easy, because now we got labeled events related to component changes. Um, and so this allowed us to create good context and knowledge around that cleaned EDR data that we were just talking about. So basically, you have operational data, which is now coming in together with your maintenance data, and both of them together is what creates value over here. Another thing is, So in our system, this is through the Prescient designer. By the way, all of this was done through the Prescient designer, and we have a low code system to do that. It's literally a drag and drop system which allows you to do a lot of these things very quickly as compared to traditional means. And the second thing is we have an event generation technology which basically allows you to create major events out of well, any big thing that has happened. For example, up till this point in time, your particular component was off for a certain amount of time and things like that. So you have all of these things quantified into events instead of just going over your entire time series data all the time. So this event generation platform just made that machine learning approach a lot easier. The big advantage over here was it actually reduced our computational load by a factor of more than 3000. So basically, and we keep reusing these events even when you have intersecting timelines for particular components and things like that. So overall, it just makes your system a lot more easy to digest instead of just a huge data lake from which you're pulling and just pumping data into an algorithm. This also, the other advantage over here is this event generation step allows you to put in context from subject matter experts, which was very necessary since this was a pretty niche topic. Apart from that, so this particular logbook system that we were just talking about, the really great advantage of this was the fact that you could have field experts who were just feeding data in here, which was extremely helpful. Followed by this, then after this data was created, we had a bunch of models we tested. The whole focus of this particular system was uh, number one was interpretability. Number two was um, the ability to refresh it, and it needed to be a lightweight model since we needed to refresh it fairly often. After doing a good amount of analysis on this, we settled on a polynomial regression approach, and we forested it. So the whole point over here was uh, since we used a small number of regressors over here, it was fairly interpretable. Um, if this system wouldn't have been interpretable, it would have been very difficult to encourage adoption across those multiple fields. Since we could explain what was happening, why, where, how, and deep learning made it extremely difficult to follow this approach, so we had to rule out that. The other thing is now after even when you go into a polynomial system, the problem is considering we are using polynomials, you always had extrapolatory risks associated with it, and we had to sort of construct in such a way that none of that risk was being transferred into the real model. And apart from this, then um, we had our model sort of needed to refresh as your components keep getting changed. So heavy models make it very difficult to refresh it very quickly. This kind of just takes care of that. So you can actually look at our system over here. This is a retraining loop, but it also makes sense for refreshing as well. When you consider it as only new data that is being pulled in and refreshing over your existing model. So you have your data organizer, which works with all the data that you have on the top. You have your model manager. This is our system, which makes sure that um, your your model is updated time to time. It is production ready. If it is making mistakes, all those outputs are logged. The ability to update the model, the ability to modify the model, as well as scale up, scale down when as and when necessary. So this really took care of a lot of orchestration problems which we have, and our system in Prescient made it very easy to do that. So this was followed by, now of course you have your entire training loop over here, which allows you to refresh very easily. Um, so you do need to orchestrate for new resources so that you can train that model. Um, you have a data ingestion system which interfaces directly with the systems on top, and then you can initiate your refresh. Now after this, we have model execution. So the whole point of this was creation of that model, but the difficulty was trying to make sure that we can keep all of this relevant. The problem is models do lose performance over time, so we needed a good refresh cycle for that. And since this was a production ready system over multiple rigs, we couldn't just have a dedicated compute instance ready to take care of this. We had to do it in an inexpensive and efficient manner, which we did. Apart from this, thanks to the rest of our tool around it, which is a digital twin, uh, we actually kept getting feedback from the loop, feedback from the field, which made we had a very reliable feedback system because of that, and the feedback loop was closed. Hence, apart from this, um, so the model itself alone, it doesn't really bring out your maximum possible value for the customer. What you do need is a system around that which allows you to observe why what is happening, how things are working. And apart from this, so we also have the ability to sort of continue to evolve this model. New data comes in, new type of data comes in, we can integrate over multiple sources. And as drillers continue using this model, they keep entering more and more log data, and that essentially keeps increasing our usable data set. Um, so this, along with the ease of use with the model manager seen here, it makes the entire system very easy to use. So this really does help. And overall, so this is how that entire system came together for production. Uh, it is in production right now. It is across 50 rigs at this point. And the beauty of it is it's very easy to maintain. A lot of this is very easy to create through the Prescient designer and all the features we have available there. It allowed us to integrate multiple data sources very easily, clean them out, build models fairly easily, create a platform along which the model execution was guaranteed, and you don't have to dedicate an entire team just to model perform, just for model performance here. Your drillers themselves are the people working on the field themselves are very well involved with the training system as well. And there's a clear space for subject matter experts to inject their knowledge in here. So overall, this is what the entire solution looked like, and this allowed us to iterate over this project very, very quickly. If you have any more questions, feel free to email us. Thank you.